Hi, everybody. Let's wait another couple of minutes for everybody to show up. I think we have already a good crowd. Okay, I think that's a good time to start. So, turning off the video camera. I'll share my screen. And move on with our discussion today. What we're going to do today is start our discussion on what we call system identification. It's a nice buzzword and an important one, actually. And in the notes, in fact, in the syllabus, there are two textbooks that have this title, System Identification Theory for the User by Leonard Lung. It's probably more advanced than we care for. And there is another one by Soderstrom and Stoica, and I apologize to my Swedish friends for my misspelling Soderstrom. There is, I think, something like this here or something like that, but we can Google that name. My apologies for misspelling it. This is an excellent textbook, and it's free on the web, actually, so you can get the PDF. It takes the reader by the hand slowly and starts building up concepts and calculations and so forth. This is not, of course, a course on system identification. So we'll try to just mention what is immediately usable and what are some important concepts so we can do system identification well. Before I do that, let me mention also the following. We already have enough material covered so that everybody can do homework 1 and homework 2. Now, homework 1 and homework 2 are necessary, but perhaps not sufficient for everything we have covered. There are also old exams. I would say, please don't wait until the last minute so you can find an exam like the previous ones when we take our exam. This is a good time so you can start from the latest first exam and go backwards so you can see what topics are of interest in covering in these exams. There is some repetition, or although no exam is exactly the same as other exams before it, I always prepare a unique exam for every case, for every year that we offer the course. Some of these exams are actually from real projects that we did in industry. There are real processes, maybe not real data, because data is proprietary, so we cannot touch the data, but the essence is there because the exams refer to real processes. So please start doing these so they can get familiarized and not be lost in the avalanche of material. There is plenty of breadth in this course. We try to keep it manageable by focusing on what is important. There was a question? That's a good question. So I'll try to keep this material out of the first exam so we can concentrate on the overview that we did, plus discrete time systems. So that doesn't mean you shut off your absorbing capacities at this point. It's interesting material. I'll try to make it as interesting as possible, in fact, with live demos as we go along. Okay. Also, if you have any conflicts with the dates of the exam, please do let me know. It's going to be a take-home exam, so you'll have enough time.
Did you already set the days from that we decided a while ago?
It was as I put it in the schedule, yeah, in the syllabus. I didn't hear any strong objections, so I believe we're going with these dates, right? I'm flexible on these. If anybody is inconvenienced, no problem with accommodating such people. This is a course for working professionals, so invariably there may be conflicts. Okay, good. So let's go back now to our technical discussion. Again, we are now starting a new PDF with lecture notes. It's called Identification, and in lecture notes Spring 2024. And in particular, we're going to deal with what people call system identification. What is system identification? Well, what do you identify? Well, you identify a dynamic system. So you build a model, and the model relies on some data that you have available, either historical or uh, deliberately generated through an experiment. So system identification or system ID, that's another buzzword that people use in industry, simply means data give you a model. Now, along with that, there may be also prior knowledge and experience, as we're going to see in the notes that we're going to cover. So it's not just blindly from data. You're allowed, in fact, encouraged to use whatever else you know about a process so that you can build a good model. And then what do you do with that model? Well, you design a controller. Okay, from that model, you build a controller. And how do you build a controller? Well, there is theory. What theory, for example, could you use? You could use Ziegler-Nichols. You could use IMC. Those are two basic classes of methods that we mentioned. And you could also use simulations. Simulations, not just today, but for the last few decades, actually, have been trivial for simple controllers or even entire control systems because computers are extremely powerful for these simple tasks. So trial and error is exceptionally useful. And we have done part of that. Remember, we had our favorite reactor. We tried controllers, tried to change the structure of the controller, the values of the parameters, and so forth. Here, we're going to concentrate on this. How do we build a model? We have seen part of that, and that's what in the notes is designated as simple ad hoc methods. We call these ad hoc methods because through clever tricks or rules, one can use intuition to quickly get results from available data. For example, in the first ad hoc method on page 3 of the notes, you can get a simple first order model for a first order system by simply doing a step response experiment. If you have the input U, the manipulated input U to your system, and the system is first order, so your control variable responds in a certain way. You know, if this is time, you know the nature of the response, so you can quickly say if this change was of magnitude m, and this final value is y at infinity, you know that the model, which is going to have a steady state gain and a time constant tau, and you can represent the model either in the Laplace domain as a g of s or p of s, or in the time domain as a differential equation. In fact, I should say these are equivalent. So you can find k by simply taking y at infinity divided by the magnitude. And the time constant is such that if you have the overall response here to be something, you take 63% of that. Actually, I should put it here, 63% of the total response. And this is the corresponding time constant for the system. So the time constant is at the point where y at the time constant over y at infinity is at 63%. Simple rule of thumb. This is used not just for control purposes, but in all kinds of dynamic systems where the response is a first order. First order systems appear quite frequently because whenever you have a conserved quantity such as mass or energy or momentum, you have that accumulation rate is equal in minus out. Accumulation rate of whatever quantity is the first derivative of that quantity. And this is a function of something that has this quantity in perhaps, or values of that quantity, and values of that quantity out perhaps, and so forth. So overall this, sorry, let's just remove these and just keep it simple. So there will be other things that depend on this quantity in a volume over which you do your mass balance, and this gives you the first order system. Very simple. I've seen this before. I'm not going to repeat it again. Now, when I have such a system, we know how we can go to a discrete time equivalent, a discrete time counterpart that says yk plus 1 is ayk plus buk is okay. This is a first order. Actually, let me do it this way. So yk plus 1 is ayk plus beuk. That's the counterpart of the differential equation. It's a difference equation. And we can get, if we call this, let's make sure we don't confuse things, P of S. In continuous time, we can get G of Z in discrete time. We'll learn how to do that. It says 1 minus e to the minus t over tau, Z minus e to the minus t over tau. This is just mechanistic, busy work. We don't have to know anything about complex integration, integrals, calculus, or anything like that. It's just a set of simple rules, 4 in continuous time, 3 in discrete time. So we can go back and forth from all of these, from this to that, and then to that, and to that. I can easily go around this without any difficulty. Okay, we have covered all of this. Of course, we may have more interesting models because first order systems exist in various places, but very frequently have higher order systems. Why is that? Higher order systems come from processes that have more than one conserved quantity. For example, you may have mass and energy as in a reactor, right? Or you may have multiple stages in a process, as in a distillation column. In that case, you will have higher order processes, and higher order processes can be identified again from data. A simple experiment would be a step response experiment such as this. It's only that for a step response experiment, if you make a step change of magnitude m for your input over time, the output may behave like this, which you approximate by first order plus time delay. You have explained how we can get a model of the form, again, P of S is equal K times plus 1 as before, except now we have a delay term. This is what we add to the previous one. And from these, We have already explained how you can get a corresponding function in the Z domain, how you can get a differential equation. Which has this delay. That's the only thing that we have to add. We can get a discrete time counterpart, which is going to be yk plus 1 is equal a yk plus b uk minus a delay term, where this delay term is this theta over the sampling period. And there may be also a discrete time transfer function, which is the same as before. And there is an extra z minus d that gives us all of the dynamics that we need in the system. I'm not going to spend much more time. This that I have already covered in both continuous and discrete time. So all of these are formulas which one can use easily using recipes. By the way, we have also given formulas for how to calculate A and B given K and tau. So A and B, again, A and B given K and tau. We can easily find these, go back and forth from these. Continuing the notes in section 1.2 on page 5, I talk about second order models. The second order model is one which may have a second order transfer function or a second order differential equation. And again, in the response of that system, we typically distinguish two cases. One is when we have a system that is called overdamped. This is jargon borrowed from mechanical engineers. So you make a step change to U, you have the response to be something like this, a second order response, which has, it's a curve that has an inflection point. Where, how do you approximate this? Well, use this. There's not much more to be said here. Of course, you could approximate this by trial and error using a pure second order response. That is certainly doable. Or you could use formulas in textbook sheets. I don't even recommend because it's not worth it going through that level of detail. Simple idea, use first order plus time delay, or use simulations for second order. Trial and error will give you a good response. It's good enough. That's what I'm suggesting in the notes. In the notes also, I'm saying a few things about how to perhaps approximate second order models for underdamped processes. These are processes where you may make a step change in the input. So it's of size m in the manipulated input. And the process now has a response which is something like this. In that case, one can quickly get, well, first of all, the gain of this process, this is a transfer function P of S, which has the form K tau square plus 2 zeta tau S plus 1. The steady state gain is easy. It's as always calculated by y at infinity over m. So if you ever do an experiment and you get something like this, fairly easy. Incidentally, when would you see such oscillating dynamics? Well, for chemical engineers, these oscillating dynamics are not very common. You may see these in reactors. That's the one case where those may actually be there. or they may be induced by feedback control. You may have a simple overdamped process. Sorry, yes, overdamped process, but the feedback control creates these dynamics, and you may have to identify this entire closed loop like this. If you see something like that, the gain is easy, and then you have two more parameters to estimate, tau and zeta. Well, those parameters can be estimated by the following simple inspection rules. So let me name the points here. So this is C, B, A, D, and E. A and E are the points where you get the maximum of these peaks. And it turns out that you can easily get zeta, this damping factor, which in this case will definitely be less than 1. That's why you have the oscillations. You know this for sure. So this damping factor can be shown to be equal to be obtainable from an expression that is given by the so-called overshoot. The term overshoot is generic. Remember we said when we talked about the Ziegler-Nichols tuning rule, Ziegler-Nichols creates a closed loop that exhibits a little bit of overshoot. What is overshoot? Well, if I have here an input that is a step change and it drives my output eventually to this value, initially the output overshoots a little bit. That's the overshoot. Ziegler-Nichols creates closed loops which have higher order dynamics, and they have a little bit of overshoot. And also there is a thing called the decay ratio. Decay ratio, not ratio. It means these oscillations decay in the ratio of this over that. So it's dE over AB or BA. This is the decay ratio. The overshoot, by the way, is defined as AB divided by BC. So the overshoot is this divided by that. And decay ratio is this divided by the red one. And again, let me remind you one more time. Ziegler-Nichols, the Ziegler-Nichols tuning rules create closed loops which exhibit higher order dynamics with decay ratio about 1/4. Green to red for the closed loop is about 1/4. Okay. But here for identification purposes, we can use either one for identification to do the following. You can show that this is E to the minus pi zeta over square root 1 minus zeta squared. Or this is equal to this previous one square, 2 pi zeta over square root 1 minus zeta squared. So calculate the overshoot or the decay ratio, whichever one you prefer. Usually the decay ratio is more accurate, more precise and more accurate than the decay ratio, but either one can be used. And then solve for zeta, you get zeta. So from either one of these, you can get zeta. And then from the frequency of oscillations, you can get the period of oscillations, and then this period, let me call it P actually. I call it T in the notes. This period P is 2 pi tau 1 minus zeta squared. I'm mentioning those zeta, you know, so from this you can get tau. So here it's zeta that you will get. And from this you'll get tau. You'll get zeta from above and stick it in here. Okay. I only mention these things for completeness because these are things that one can actually use easily without knowing much of the theory. Those are well-known formulas and not very frequently used, only occasionally. More frequently used is the following. In section 1.3, we are talking about any order models. So these are neither first nor second nor third order models. They can be any order, they can have any dynamics. It turns out that one can build such models which have the following form. Yk is equal to a weighted sum of past inputs. So past inputs are k minus I. So if my current output is at time k, past inputs are k minus 1, k minus 2, k minus 3. In fact, there may be a direct effect. So there may be a I equals 0. So you have here the sequence uk, uk minus 1, uk minus 2, uk minus 3. So I in general goes from 0 to infinity, all the past values of these inputs, and they are weighted by certain weights. Those weights are sometimes called the convolution weights, HI. And for stable systems, we get that Yk is very well approximated by a sum from 0 to n, a finite number. So this is now finite rather than infinite. And this is because hi go to 0 as I goes to infinity. So this is what creates that. In other words, if I plot these coefficients hi, I get values which may be something like that, but they die out as I go like this, right? These values. This is notice that this has a direct effect of the inputs on the outputs. That's the advantage of these models. These models have directly the effect of inputs and outputs. The disadvantage is that they may have many coefficients to estimate. Order of magnitude in industry, say 30 to 50. Do people actually estimate those coefficients? They do in step response experiments, and there are some clever tricks that one can use to avoid the problems of having to estimate so many coefficients from very rich data. So one thing at a time. First of all, let's gain some appreciation for what those mean. Before we do that, one historical remark. These kinds of models became very popular during the early days of model predictive control. There is a famous paper that I mentioned in the notes, and if we Google it, it'll come up immediately. So Jacques Chalet, heuristic predictive control, Automatica, published a seminal paper, which was a paper that introduced model predictive control. So, and it's called model predictive heuristic control. You see it has about 2,000 citations. Well, no, 3,000, over 3,000 citations. It's a historical paper that ushered in the era of model predictive control. And in that paper, clever engineers came up with the idea that you can do all these things. So you see the abstract is available. You can read it easily from its source. In that paper, these engineers said, well, things in a chemical plant are optimized at steady state. But steady state concerns long periods of time. My plant is actually never at steady state. So yeah, I can average things and say if my inputs are on the average at this value, the output is going to be at this value on the average again. This is what happens in chemical plants over long periods of time, say over one shift going to another shift to another shift. So shifts can be 8 hours or 12 hours. Those are standards in industry. So from one shift to another, I may have roughly steady state values, give or take. And people optimize these steady state values by a technique called real-time optimization, or RTO for short. This is usually done over steady state. And over steady state, you have actually full nonlinear effects of inputs and outputs. And that's why you need a process simulator. And then you use your process simulator to do optimization and find the optimal settings over an entire shift. Now, during that shift of 8 or 12 hours, things fluctuate, and your controller should select optimal settings for the manipulated variables. These people thought about that long and hard, and they reasoned as follows. Well, when I have shorter time periods, say hours or minutes, then I don't have things at steady state. I have things that vary. And my current output value does not depend on a single input value or a single value of my inputs. It depends on many values of my inputs. In fact, on many past values of my inputs. Well, I'll capture that effect by using this kind of model. All the past values of an input, assuming there's only one, in fact, there are more. Let's stick to one to keep things manageable for now. There are going to be multiple of these input values that are going to have an effect on my current output value. And as I go more and more to distant and more distant past, this effect should become smaller and smaller if my system is stable, which is why I'll use this kind of simple model with a finite of past values. This model is called an FIR model, as I'm indicating in the notes, and FIR stands for finite impulse response model, or FIR. What is the meaning of this? Well, first of all, it's called an FIR model because this model actually corresponds to what I see, so to what the response of my system is, if I throw this particular input. So if I have a model that has an input U and an output Y, then these coefficients HI in my model are actually going to be the values of the response, the values of YI, if I throw to my system a finite impulse. The term actually finite impulse comes from continuous time. For discrete time, one should rather use the term finite pulse. But the term FIR, or finite impulse response, is universal, so it's used universally both for discrete and continuous time. So we'll use it here universally with the understanding that this is for discrete, impulse is for continuous. So let's say an example. So first order system, y, k, plus 1. The next value depends on the previous value plus of the input, of the output, plus the previous value of the input weighted by A and B. We have seen how we can get such a system. For example, we've seen all the long chain of derivations, so we can understand where this is coming from. Remember, for example, if we had a first order heater, we could get a dynamic model that is first order because accumulation rate is equal in minus out. And then we get a first order ODE, and then we can discretize the ODE and get a first order difference equation. I'm not going to repeat the exercise because we have done it already several times and it's in the notes. But taking this as my model structure, I'm going to see how this system responds. So we're going to see the response to a finite impulse, And in fact, it's in discrete time, so it's a finite pulse. So my input is going to be a finite pulse. Well, finite actually refers both to the impulse and to finite response. So this is a finite impulse response or a finite impulse response. What is the difference? Well, the response is finite in the sense the response doesn't blow up. The system is, again, stable. So this is a finite impulse response or a finite impulse response, right? A response to an impulse of finite power. It's not an infinite power impulse. Let's say this. So this is a stable process again. Remind me again, for this model here, what is the one and only one requirement I can have on these parameters so that this can correspond to a stable model? Well, let's try to do this together so we can remind ourselves. So I start with y0, and then I'll compute y1, which is going to be ay0 plus b u0, correct? Well, let me compute y2, which is going to be ay1 plus b u1. And now I'm going to plug in y1 from above. So it's going to be equal to ay0 plus b u0 plus b u1, which is going to be a square y0 plus ab u0 plus b u1. Let's take at least one more step so you can see the pattern, and then we'll generalize. So this is going to be, help me with this. Dictate to me what I should write from the model. Yes, plus BU2. And what am I going to do with Y2? Yeah, plug it in from upstairs. So this is going to be A square Y0 plus ABU0 plus BU1 plus BU2, which is equal to A cube Y0 plus A square B U0 plus AB U1 plus B U2. And I will keep going. You see the pattern now. If I have y1, I have a to the power 1. If I have y2, I have a squared times y0. If I have y3, I have a cubed a0. So you can tell immediately that if I go yk, I'm going to have a to the k, y0, plus other stuff, which I can write, but I don't want to bore you with algebra. You get the essence of this exercise simply by looking at this term. This term, as k goes to infinity, this term will go either to infinity or 0, depending on what? Is that again? No, k goes to infinity. So as k goes to infinity, this term yk will go to this, which will go to infinity or 0, depending on what? The value of a. So if a is 1/2, is this going to go to 0 or infinity? 0. If a is 1/4, 0. If it's 0.9, 0.99,
So if it's less,
if it's less than 1, it's going to go to 0. Okay? So if a is less than 1, it's going to go to 0. And if a is greater than 1, it's going to go to infinity. So the one and only one condition for stability of this model is equivalent to a being less than 1. The magnitude of a is less than 1. This makes sure that there is a finite response. So it's a finite response to a finite impulse, to an impulse of bounded area, or to a finite pulse in this case. Let's do the simulation by hand to convince ourselves that this works as intended. So I'm putting this background exercise here, and we'll throw to this system here, a pulse. So UK is going to be this pulse. Let me draw it first. So this is 0, this is K, and this is UK. 0, 0, something, and then again 0, 0, 0, 0. So these are the values of UK. Of course, in continuous time, this will be kept like this in my system, and that's why we call it a pulse. But as far as the points are concerned, I have 0, 0, something non-zero, 0, 0, 0, 0. In fact, let's make that a unit pulse. So I'll make that equal to 1, just to make my life, keep my life simple. So let me write it in words, in formula here. U sub k is 1 if k is equal to what again? 0, and it's 0 for all other values. Okay. Let me assume that my system output is initially at 0. This has been at steady state. So input has been 0, output has been 0. So I'm going to observe how my system behaves. So if I throw this input U sub k to my first order system described by this equation, let me observe what I'm going to get. So I'm going to get y0 is equal to 0. That's my starting value. y1, so I have k equal to 0, 1, 2, 3, 4, etc. y1 is going to be a y0 plus b u0. So this is going to be equal to, help me with this. So just b u0, right? And u0 is what? 1, so just b. Okay. And then let me put it here actually to save some space. And then y2 would be a y1 plus b u1. So y1 is this. So help me with this. AB, right? And then y3 is equal to what? A y2 plus b u2. Help me with this. A squared b, and you see the pattern now, right? It's fairly straightforward. So for this experiment, yk will be equal to what? A to the power k b. And now it's fairly clear that if you actually write your model as y k plus 1 is sigma h k u k minus I. So this I goes from 1 to n. If I throw this input to my system, I can also observe what I will get for y0, y1, etc., etc. Let's do it together. Y0 is going to be what value? It's equal to 0. Y1 is going to be equal to, let's do this together. This is for k equal minus 1, for k equal to 0. Y1 from this expression is going to be the sum of I, apologies. So it's going to be the sum of HI. Let's do it. Well, let me write it first. HI U minus I. I goes 1 through N. So which ones are they? For I equals 1, I get H1 U minus 1 plus H2. Tell me this. Let me make sure I do this right. Sorry, let me, apologies. I have an extra one here. So let me do it like this. This is 0, this 1. So let me do it like this. This is better. Apologies on this. So for I equal to 1, this becomes 0. This becomes minus 1. H3 U minus 2 plus all the way through Hn U1 minus n. And what is the final number for this? U minus 1 is what? Yeah, 0. U minus 2, 0. So all of these disappear. And what is U0? 1. So what is the final result? H1. Okay, let me continue with k equal to 2. You get the pattern now, right? So this is going to be sum. I goes from 1 to n. HIU 2 minus I is equal to H 1. What again? 1 plus H2 0 plus H3 U minus 1, etc., etc., etc. And you have, what is this? U1 from up here. 0, yes. What is this? 1. This 0. All of these are 0 here, and we get H2, and you see the pattern. Y sub k in general is equal to HK. So the model is called finite impulse response because the response is finite, it doesn't blow up, it's a stable system, and the response is such that Y1 is equal to H1, and Y2 is equal to H2, and YK is equal to HK. And it turns out actually that those coefficients here can be used for any system, such as a first order system, for which we found what is the correspondence between H1, H2, H3, etc., HK. So for a first order system, this is H1, this is H2, this is H3, all the way through HK. In practice, what people do is actually throw an input to the process and calculate these coefficients experimentally. That's what I throw in page 6 of the notes on figure 5, which requires some explanation what is happening there. First of all, let's prevent a misunderstanding about what is the kind of experiment that one does to get these coefficients H1 through HK. In fact, let me get some ideas. How would one get these coefficients H1 through HK? For example, let's say that our model is first order. I can represent the first order model in the classic form that I already mentioned here. Let me square it. Here's my example of my first order model. It's stable. I can represent it like this, or I can represent it like this. Whichever way I represent my first order model, I know that these blue equations in the blue boxes are equivalent. And I'm interested in these coefficients HI. I can get these coefficients HI through this by throwing an impulse, or a pulse rather, my system and looking at the response. Or I can do some other kind of experiment, or whatever experiment I do, I can get the response like this, or I can get this model structure in whatever experiment I do again and get A and B. Any ideas on how I could get these coefficients HI by doing an experiment? Well, let me throw some help here. First order system, correct? Is there a continuous time model that I know how it relates to this? Yes, and I can go back and forth. I know the formulas, okay? So if I did a step response experiment, could I get the continuous time model easily? Yes, okay. Could I then go from the continuous model from gain and time constant, get A and B? Yes. And then could I use these formulas to get H1, H2, H3, HK? Yes. So I could easily get my coefficient. This is doable actually, and people do it in practice a number of times. And why don't they stick to this model and they go to that model? Well, they don't stick to that model. They may go to that model because for optimization purposes, this may be easier to handle. We'll see this when we do model predictive control. Okay. But all of these are different facets of the same coin. Which only has two, this may have more actually. Other experiments that one could do. Well, maybe I could do just a pulse response experiment, not a step response experiment. I could do this kind of experiment. I could throw this pulse to my system, look at the output, and then get these coefficients. Would that be a good idea? Any ideas in this discussion? So I could throw, I could throw this input, 0, 0, 0, this is UK, 1, or whatever magnitude, and then 0, 0, 0, 0, 0. And I could observe the output, and whatever output values I would get something here, that would be 1, and then I would get another value, and then another value, and if this is YK, I know this would be the value of H1, this would be the value of H2, this is the value of H3, etc., etc. In fact, this is generic for any order system. We just demonstrated upstairs that for any order system, you don't need to start with anything else. Give me the structure, this FIR, the response to a pulse gives me these coefficients. Is this a good idea or not? From a practical viewpoint. Well, let me explain where I'm going with this. In practice, you never get a nice clean response like that. There is noise in your measurement, right? So this coefficient, this response of HK at the first time point, 0, 1, 2, 3, 4, 5, 6, 7. This response that we have here, in reality, it might be here. And the second response, in reality, it might be here. The third one might be here. And the noise may be here, and here, and here, and here, and here, here, and here. So you may get a fairly non-smooth type of model, which you might try to smooth out, to smoothen it after the fact. But this is a weird model, right? And here I'm simplifying things. In reality, people don't have 5 or 6 coefficients. As I mentioned, people in practice have 30 to 40 to even 50 coefficients. So they can go far enough into the past and get good values. So a pulse response experiment, so this is a pulse, is not a good idea. That's not what people do. People do other experiments. Perhaps they may do a step response. So pulse response, it's what we use theoretically to understand what this model corresponds to. The coefficients HI correspond to the pulse response of this model. But in reality, a better experiment is to do a step response experiment. And then there are other tricks that one might do, but let's stick to the step response experiment first. So I wouldn't throw this. I wouldn't do this. I would try to do something else. I would throw a step to my process. Why would a step be better? Well, let's try to see here why this might be a better thing. So I might throw a step here. So now my input, my process, I'm starting with a process at steady state and throwing now this input there. It's a step of magnitude, let's say 1. Okay. And now I can observe my output. And my output yk will now respond something like this. Make it a bit more interesting. So it will respond like this, and will eventually reach a steady state, but it will be noisy. But let's just go through these clean, smooth lines to see theoretically what we would expect. Let's do the same exercise that we did before. I know it's going to be tedious in algebra, so let's take a deep breath and see what we get here. Okay, so let me write first what is the input. UK is the input. It's 1 when k is greater than or equal to 0. It's 0 else. Initial value, it's 0. Y1, it's going to be equal to, according to our model, right? So it's going to be, well, let me write the model so we can have it handy. So k equal to 1. For k equal to 1, I have y1 is from this model, h1 multiplied by u what? 0, yes, plus h2 multiplied by minus 1, yeah. And then h3u minus 2 plus, and these are all 0, right? All the way here. So the final result is this is 1, so this is h1. Then 2 get V2 is H1. And then help me with this, U K equal to I equal to 1. First term has U sub 1, yes, plus H2 U0 plus H3 U minus 1. And this is 1, this is 1, this is 0. So everything else is 0. So what is the final result? No? Yeah, H1 plus H2. And you keep going. So K equal 3 will give me H1 plus H2 plus H3, and I'll keep going like this. K, general K will be H1 plus H2 plus. Now, in fact, the final K that I will have is an N, which is going to have Hn, right? After that, I assume the H values are equal to 0. So now you see that H1 is the value of Y1. H2 is Y2 minus Y1. And then H3 is Y3 minus Y2. And that's a simple way to get a step response experiment that you would do anyway and get values of these coefficients. The interesting thing is that when you have data here that are noisy, so you may have here this noise, 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 sorry, noise, noise here, at least for most of these coefficients, you can draw a straight line here as you go. This, in fact, you can take a somewhat exponential response with 1 or 2 exponentials after a dead time and fit all the data here by the simple exponential and try to smooth out things, right, for these coefficients here. There are many other tricks that people use in practice to avoid noise, but we'll stick to this for now to avoid being bogged down to details. Quick summary of what we have done now for our FIR models. So we said there are first order models, easy, step response, you get the model. There are second order models, easy. If it's just second order overdamped, first order plus time delay is good enough. If it is underdamped, still you can get everything by inspection from overshoot in a period of oscillations. No big deal. Yes?
I started water.
Say it again.
I started 0.
Here?
Yeah.
Oh, yeah. I said there may be a direct effect. For I equal to 0, that says Yk is equal to H0 UK. So at this very moment, the input has a direct effect on the output. In most instances, that is not there. So to keep things a little simpler, I just said, let's assume that there is no direct effect. Okay? Because it's hardly ever possible to transmit an input in 0 time to the output. There will be a little bit of delay. So try to keep things simple and not be bogged down to these special cases. So in my summary, then I was saying that we can first, second order systems, ad hoc methods, simple, continuous time, discrete time, no big deal. Finite impulse response models are interesting because, and they're used in practice quite a bit, although their identification is more elaborate. But nevertheless, the big plus of these is that here you don't have to assume the order of the system at all. It's not first order, second order, any order. Just the direct effect of the inputs on the outputs. The drawbacks are, A, this is only for stable systems. Well, that's not a big drawback because most systems we deal with are stable. They're designed to be stable for safety reasons. That's a small drawback. The bigger drawback is you will have too many of these coefficients, so you'll need a ton of data to actually identify those, estimate those well. Okay, but there are tricks which we are going to see how to use, and I already mentioned one. If you do, for example, a step response experiment, you can easily tell that these, you can fit here a smooth exponential response and get things fairly easily from these coefficients, and you'll sacrifice some precision here, but you get a lot of better estimates, and you improve precision that from that view. Sorry, you sacrifice some accuracy, but you improve the precision by using this smoothing. We'll see more about that after we have talked about least squares. Let's move on a little bit to section 1.4 to mention something on page 7, to mention something that is worth knowing, because these things appear all the time in control systems. And like I said several times, computers love indices I, J, K, L, and then they don't care about that. Give them as many of those as you want. They execute tons of calculations faithfully. We humans have difficulty looking at indices. We can look at continuous images a lot more easily, and patterns, verbal or visual. Nevertheless, I'll mention these models because I'll tell you what they do verbally so we can get around the multitude of indices that we have here. So there is an alphabet soup of these models that we said, and I'll show you a few in example 1. Example 1 talks about linear dynamic model structures. There are some with exogenous inputs, without rather exogenous inputs, and some with exogenous inputs. So with exogenous inputs. Systems without exogenous inputs are what people call time series, which are important because frequently we just have to deal with this situation in practice. Let me explain how. So we have a closed loop control system. There is a set point that doesn't change. There is an output. Let's just keep it 1. And there are disturbances. Disturbance 1, disturbance 2, lots of disturbances. Well, this is a system which essentially looks like this. If I look at this system, the output behaves like this over time. If the set point is not changing, it's fixed, right? So this is the value of the set point, or in deviation form, this is the 0 value. And my closed loop behaves like that. Why isn't the output exactly at 0? Because there are disturbances. Okay? There are random disturbances. Disturbances may be up, down, steps, white noise, Gaussian noise, all of the above. Who knows? Okay? The control system, so this is a closed loop system here. The control system keeps the output at its set point. A way to model this is by using some of the models I'm going to mention now. These models do not have any so-called exogenous inputs, just noise that drives this output to be here. These, again, are called frequently time series. This is jargon, by the way, that economists love, because in an economy, there are very, very few manipulated inputs you have. The Fed, for example, has only one manipulated input. What manipulated input does the Federal Reserve Board have to control the economy? The Fed, the Federal Reserve Board, tries to manipulate 2 variables associated with the economy. Those are the inflation rate and unemployment rate. Right? And it has only one manipulator. What's that? Yeah, exactly. The interest rate, the prime rate. It's a mind-boggling control problem to solve. First of all, you have one manipulated variable, 2 outputs. And you have 350 million states because you have all of those individuals. And it's a system of incredible complexity. People have been working with this for a very long time, trying to figure out how to do it. It's a challenge. So the miracle is that it works rather than there are snafus every now and then. Okay, so people then they describe this system as time series because if you don't change the prime rate, everything is fixed there. It's just random shocks that give you things that happen there. So with time series, you can have this form. This is called autoregressive. It's autoregressive because you regress yk on itself. So you take a weighted sum of past values, y, and you say the current value of the output depends on previous values of the output plus exogenous, not exogenous, sorry, plus random noise. This is noise. And the way I have written it here, it's typically considered to be white noise, but there may be a model for this noise. Then there are other models that say, well, the current value of the output is actually just the effect of noise. This is called a moving average model. So this is white noise. Again, this is the effect of noise. And of course, you can combine the two, and you have AR and MA. So you have the ARMA or ARMA model that says the current value of the output is a two weighted sums. One is the weighted sum of it's the same output, 1 through n, let's say, and the other one is a weighted sum of white noise. This is just another structure. And of course, you may have the autoregressive integrated moving average model, because remember, all of these are stable. There is never anything going to infinity. Well, in practice, for many processes, things may drift slowly to infinity. So it's not a blow up, but it's not a return to steady state. This I basically says that I'm integrating something. So the general form is just like ARMA, so yk is the same as above. But there is a thing that says the roots of the characteristic polynomial, which is bi z to the minus I. If you take z transforms, which we know how to do, and you take z transforms of this ARMA model, this is going to be y of z, and this is delayed. So each one is going to have z to the minus 1, z to the minus 2, z to the minus 3, right? Because it's delayed. So you have the coefficient times z to the minus 1, z to the minus 2, blah, 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 blah. So this equation has a pole at 1, which means this is drifting. It integrates values. Okay, so there is a drift here that it goes up and down. Not everything settles back to steady state. Chemical processes actually on occasion have this behavior of slow drifting. So ARIMA models are used. There is more to this alphabet soup, actually. So there are all of these models that I mentioned here. You can add an X here and make it ARCS or MAX or RMAX or ARIMAX. Okay, well, let me just write one. Let me write an ARCS. So an ARCS model is going to be just like AR, but there's going to be an exogenous signal, right? So it's YK is, I'm just going to copy that stuff here. Sigma BI YK minus I goes 1 through N plus EK, and there is an exogenous signal. The exogenous signal is the U input that we typically have. So let's call this AI UK minus I goes from 1 to N. And of course, I have all of those going from 1 to N, but in practice, this may be different. It may be a different thing. And you realize now what it will take to write an RMAX. I'm not going to do this. Okay, you can do this for fun if you want. Just add this term here to the ARMA model, and you can have an RMAX model. So you can add this term to the RMAX model and so forth. Why do we bother mentioning all those things? We bother about mentioning all those things because these models may be convenient for system representation because they are what is called parsimonious. I hope I haven't misspelled parsimonious. What is parsimony? Parsimony is a property that refers to frugality of a model. What do I mean? It doesn't have too many parameters. Why? It doesn't have too many parameters. Why is the number of parameters important? The number of parameters is important because to estimate these parameters, you need a corresponding amount of data. A straight line needs 10 times as many data points, right? Well, you have two parameters, you need roughly 20 data points. If you have a quadratic has three parameters. Well, then you would need 30 data points to estimate those. Well, a rule of thumb. If you have a cubic polynomial or a quadratic, you need 40, 50, and so forth data points. If you have 40 parameters in an FIR model, you might need 400 data points, which may be too many. So over the years, it's not about computational power, it's about experimental data points. How many you need? People have been playing with these things, and there's an endless series of papers that talk about, do you use an AR or an MA or an NERMA or an ARIMA and NERX and all of these models. In practice, thankfully, you don't need to be bogged down by which one of these is the right one. Because most of the time, many of those are correct. In principle, actually, all of those are correct. How well you estimate parameters depends on how many data points you have. But there are tricks of the trade you can do so you can get around whatever issues you might have with a model that is not very efficient for the number of data points. In fact, things get even hairier if you have what example 2 shows on page 7, which is a state space model. Now you have input U, which is perhaps even a vector, and output Y, which are a vector. But even if you have a single input and a single output, still state space models are important because they capture higher order dynamics. And you have a state vector, you have a matrix here, and you have the state vector, and then you have another matrix here, along with the input vector. So this input is at time k, and this vector is at time k, and this is at k plus 1. And it says the next value of the state of the system depends on the previous value of the state plus the previous value of the input. And then the output is an algebraic function of the state. So at k, it's an algebraic function of the state. In fact, if there is a direct effect, since you asked about when do I start, if there is a direct effect of the inputs, let me be more realistic here. If there is a direct effect on the inputs, I have a matrix D, apologize in the error here, matrix D that has them. So how do I get this and this and this and this? Those may be challenging problems. They're not easy problems to solve. Thankfully, for most of our purposes, we have simple methods that can help us get models reasonably well. But to do that, we have to go beyond the ad hoc methods that we already mentioned. We're going to do that starting in our next time, when the time comes, in section 2 of the notes that says parametric methods using least squares. We need a little bit of statistics to actually get around issues that eyeballing may not resolve very well. Because we're going to see frequently you don't have a nice step response like this, the input and the output. you frequently have something that says the input was something like, sorry, like this. And the output was like this. Okay, and then inspection doesn't help you very much. But it may turn out actually this is a fantastic set of data in which you can actually build a great model, in fact, even better than the step response model that you would get from inspection. We're going to see all that starting in our next lecture.